So we're going to talk about the, first of all, talk about linear classification with perceptrons, a classification model based on linear models. And then we're going to talk about perceptron learning, right? How the perceptron apply learning algorithm. And then we're going to transition toward kind of formulate a loss function and apply gradient descent methodology to solve this problem. So let's start with this. Let's start with the perceptron learning. So just like what we did for the linear regression, so there we have this feature represented in terms of x, and y is the target value. So we're pairs of these guys here. The only difference now is that we're going to use this notation we talked about previously, use a superscript to represent the index of the samples. And right now we have samples here with I goes from 1 to n. Again, we use this type of notations. So xi, each individual input is the input here. We call them either input or call them features. So that's the same terminology we used previously. So in general, we assume it's n-dimensional, so which means contains n components of that. And different from the regression, the target value y, so in this case here, is going to be a categorical. So, however, we're going to represent those categorical values using numbers. So then, in particular, we use more or less integers to represent those categorical values. And specific choice of integers does not really matter. The choice of them more or less depends on for the convenience of the annotation purpose or because of the conventions. So for now, we're going to assume these conventions here. We start talking about so-called binary classification, which means that you only have two different classes. And it could be, positive, it could be negative, could be, it depends on specific applications. You might have, you want to develop a model to detect spam emails. So in that case, the target value would be your email either spam or not spam. So however, we're going to represent them with binary values here. So we're going to have two different conventions for representing those binary values. So one convention is using -1 +1 to represent these ones here. So later on, I'm going to introduce a different convention. But for now, assume we use this -1 and +1 convention to represent the target values associated with each sample of that. So in general, this perceptron classification problem here is you have this in the models here, your classifier here, the model received the input, x as your input here, have n features. And first of all, you calculate a linear combinations of this input here, and that is the linear response or the score function we use for the linear regression. So essentially that is this, if we use the theta here, that would be the dot product between your parameter and your input x here. So more specific, you can also write down as be a theta transpose times x here. So I use slightly updated version of the notation in the slides here. So follow my notation here because this notation will be consistent with your previous notations here. So x is n-dimensional. So for now, I already assume x has already been augmented with that constant features so that I do not need to specifically write down that bias term. So in general, I might need to write down to be θ0 plus θ1 times x1 and so on. But for now, if I assume my feature has already been augmented with a constant 1 to be the first feature, and then I can simply write down that to be a theta dot x or theta transpose x. So this is my score function and linear response. And then after linear response, because I need to make a decision whether to assign label -1 or 1 to this input here. So I need to use a nonlinear function to make that decision. So typically, common choice is to apply a threshold function. So for instance, if this is score here, fx theta is positive, and then you say, I'm going to assign label to be 1 here. If x theta is positive, and you can assign, say, y prediction is equal to 1. If this guy here is negative, you say predict target is -1 here. So that is a kind of very simple thresholding function applied to the response to the score here. And then after that, you can make a decision based on the scores here. So, so right now, I'm using these conventions here. Later on, I might use another convention to represent the target values here, to be either 0 or 1 here. So it depends on the choice I have. For now, let's assume using this convention. So this target value convention, it doesn't really matter here. They're mostly used for the purpose of simplifying the notations. And we just want to know that they have 2 classes here. I'm going to assign either -1 or +1, and in the first convention, in the notation here. So in terms of if you want to visualize the features here in 1 dimension, so you can think about it here, this is the x-axis here. Suppose you only have 1-dimensional features here, and this is the y here, right? And however, y in this case here is only have discrete values, can be either +1 or -1 here. So it's different from the previous models, +1 or -1 or +1 here, and different from the regression models. In the regression models here, the values can have continuous values. So this is slightly different here. And we say, well, in the simple case that your input has only 1 feature, that decision is very simple. Say, so the thresholding function is simply x plus a constant. So that case, right? So that in the simple case here, your scoring function here will be simply equal to theta 0 plus theta times x here. Right? So essentially, you just make a decision. Say if x is greater than that threshold, you have +1, otherwise -1 here. So that will be your decision boundary. Depends on where you place this decision boundary of that, whether shift left or shift right. So that's for 1-dimensional features. So in general, for the high-dimensional feature, you might have need to think about combinations of the input features of that. So that's the model I talk about introduced so far. It have a specific name. It's called Perceptrons. And this is a very widely used model and has been proposed a long time ago. It was proposed in the 50s. And then in this case here, the model is saying that you're going to use a thresholding function applied to a linear response. And that will be input feature combined together with weight parameter, the theta here. So that's what I talked about. So in terms of perceptron learning, perceptron decision making here, and you calculate those things in 2 steps. One is calculate this linear response, and the next, that will be first step. The next, apply the thresholding function, and after that, you can make decisions about it. And the people originally developed these models and try to use this as a simple models of biological neurons in the brain, human brain. So and neurons, they observe from the neurobiology point of view, each neuron receives input from many other neurons. So you can think about this neurons here receive input from other neurons here. This will be X1, X2, and Xn here. So this is the output neurons here. They receive kind of so-called synaptic connectivity from all the other neurons. And then each neurons might give you positive input here or negative input there. And the strength of the connectivity is determined by this so-called parameter here, theta 1, theta 2, and theta n here. So you can interpret this type of parameter to be the connectivity strength from this X1 neuron to this output neuron Y here. So you have this kind of physical interpretations of the meanings of this parameter here. They represent this, how strong is those connections. Is this strong positive, which means that this connection here will be so-called excitatory. So these neurons try to excite these activities of the Y neurons here. So if theta 2 is negative, so which means that this connection here will be so-called inhibitory. And the X2 try to inhibit the activities of the Y here. So they have this kind of meanings drawn from this biology. And that originally was, this model was originally developed, is motivated by what happens with, within the biological neuron. Of course, this is a very simple pictures of the neurons. Neuron itself is much more complicated, but in the old days, people abstract, what's the happening within the neuron. They think this is represented in the kind of backbone, what's happening within the biological neurons. So this is called Perceptron. This type of model is still used today, and constitute more or less nowadays the backbone, the fundamental unit of the neurons within the deep neural nets. So we're going to come back to this point later part of that. I just want to give you this motivation. And people proposed something called perceptron a long, long time ago. And then originally people say that, what is the threshold here? And then they try to associate it with this biological neuron, saying that, well, if you are passing, so you have this total linear response, you can treat it as if it is a total input to that neuron. So how much input to that neuron? And then essentially in the biological neuron, that would be the currents, the total currents that will be sent from the presynaptic neurons to the postsynaptic neurons. And then those total currents here might drive the neurons to pass certain threshold, such that the neuron will fire something called an action potential. So that will trigger a firing of action potential waves. And that action potential was sent through the axons, was transmitted to other neurons. So they have this interpretation of the threshold to be the point that can lead to neuron firing as action potentials. And well, that's just an interpretation here, right? So, however, we treat them as simply as a computational unit here. They simply, the computational unit would be simply say linear response combined with the input here, and then I'm going to apply a threshold function here. And then that would be my prediction, predict the values, labels of these guys here. And because it is a binary classification, so my prediction is positive, is going to be 1. If it's negative, it's going to predict a label -1 here. So that's this kind of model associated with this guys here. So I'm going to use this notation here, theta and y here. Theta, I'm going to treat it as the parameters of my models here, right? So that's the perceptual learning here. So the decision boundary, of course, as I just mentioned here, it just depends on whether this guy here is positive or not, right? In high dimensional space here, what we want to know is that, say, combinations of theta 1 times x1 here, theta 2 times x2 here, suppose it's 2 dimensions here, whether this is greater than 0 or less than 0 here. So we know that this type of decision boundary will be essentially decision boundary will be exactly at the point theta 1 plus theta 2 x2 exactly equal to 0. So this will be decision boundary. And away from the decision boundary, then you draw labels to be either positive or negative. In general, in high dimension here, the decision boundary will be the dot product between these two here. That will be in the high dimensional space. And this type of decision boundary in general is called a hyperplane. The reason it's called a hyperplane, and because it's a generalizations of this type of decision boundary from the simple geometric structures in lower dimension and then generalized to higher dimension. For instance, in a 2-dimensional space, and the decision boundary will be these guys here. Right? If you look at this guy's decision, and then will be theta 1 and theta 1 times x1, theta 2 times x2 here. And if you have a bias term, that would be b here. So that would be the decision boundary in a 2-dimensional space. And you can see that that decision boundary will be a line, because in a 2-dimensional space. So this is x1, this is x2 here. And then this theta 1, theta 2, and these are the parameters determining the slope and the intercept of these lines here. And above the line would be labeled with 1, with potentially 1 or -1. That would be below the line would be labeled with the different labels here. So that's in a 2-dimensional space. So now you think about it in a 3-dimensional space here. Suppose you have 3 features here, x1, x2, and x3 here. And then in that case, decision boundary will look like a plane here. And then for all the data points above the plane, you label with 1 class, and below the plane, you label with the 2nd class. So then you can have separations of the 2 space, half space, and the other half space. And that this type of decision boundary is linear decision boundary. And this thing here is called a plane in 3 dimensions. In a space that is greater than 3, and we tend to call it to be a hyperplane. This is the terminology referring to these guys here. So for instance, let's look at this examples here. This example is using feature in two features. So you have this x1 and x2 here, 2 of them here. So x1 is plotted here, x2 is plotted here. And now the decision boundary will be theta 0 plus x1 times theta 1. And then theta 2 times x2 here. So that's my decision boundary there. Suppose, now let's look at one particular choice of decision boundary with these parameters here. And suppose this is theta here. So theta 0 is 1 here, and theta 1 is 1/2, theta 2 is -1/2. So let's look at what this decision boundary will look like. It will more or less look like these guys here. So that in this is the be a line. Essentially, if you plug in the parameters within these models here, essentially you get something like this: x2 equal to x1 plus 2. So that this is the line corresponding all the points satisfy these conditions: x2 equal to x1 plus 2. We know that that's simply in our line here. And then this point here is 2 here. This is the intercept. And the slope here is 45 degrees because x2 equal to x1 here. So essentially, it is a 45-degree line intersect at 2 here. So that's my decision boundary here. And if it's above these guys here, and this is the regions here, will be x2 greater than x1 plus 2. That will be the space above this line. And for the other side here, this side here will be x2 less than x1 plus 2 here. And you can see that will translate into either this guys here is positive, theta dot x here. This will be translated into equivalent to saying that your parameter dot between them here is negative here. And these guys here was equivalent to saying that your parameter times the input figure is positive. So as a result, you label this with +1, you label this with -1 here. It will be negative, therefore will be negative here, okay? You can see now this kind of a linear decision boundary in 2-dimensional space. It is a line here, separate that space into 2 halves. 1 half will be +1, the other half will be -1. So that will be 2-dimensional space. In 3-dimensional, it will be plane. In dimension higher than 3, we call it a hyperplane. So that's this. Well, so that's the linear decision boundaries. Before I talk about the algorithm, how do we discover those parameters? Because essentially the direction, the intercept of the lines, and then in 2 dimension, and then the hyperplane in the high dimension spaces here. Before I talk about the learning algorithm, discover this parameter here, a few other items I just mentioned that. So first of all, so as I talk about right now, we talk about the linear classifier here. So however, in many other data sets here, some of the data sets here, you may not have a plane can completely separate these 2 groups of data points. And we have this terminology called a separability to refer to whether data can be linearly separated or not. For data set can be linearly separated, for instance, in this data set here, clearly you can find a linear decision boundary to separate these 2 groups of data points here. And we call this type of data called linearly separable. And however, for the other type of data sets here, shown in the right-hand side here, this in the 2-dimensional examples here, you can see that, and there are red dots in the middle of the blue dots here. And in this case, you will not be able to find a line that can completely separate blue from the red. So which means this type of data set is linearly non-separable. And we use this terminology to refer you whether data set is linearly separable or not. For linearly separable data, essentially what this means, there exists a linear decision boundary that can perfectly separate these two groups of data sets. For linear non-separate one, which means you cannot find any line, any linear decision boundary in high dimensional can completely separate these two groups of data sets here. So most of the problems we encounter in practice are linearly non-separable. That's very common. Most of the time, you won't be able to find a model that completely separates the two groups of points here. And there are many reasons why this is the case. And first of all, you might have the data observations here that its values are possible under both classes. It's just naturally possible to see. For instance, in the initial example we gave in the previous lectures regarding a predicted credit score based on age and income levels of that. So in that case, it just very likely that even for people with the same age, same income, and in some cases they might have a high risk, some cases they might have low risk, and so this type of data exists. And another example would be, say, if you want to classify the benign cells versus malignant cells, in many cases, from the images, many of the cases they look very like each other. So you won't be able to clearly separate these two types of cells. And that's just saying that the data set is inherently challenging for you to separate them here. The observations, they can have both labels in both cases of them. So that's very common. And the question is this, what should we do to handle this type of situation here? Well, so it depends on what our eventual goal of that. Well, so in general, you can try to improve the accuracy through two methodologies. One is try to introduce more features, and that might be possible. So the idea is that maybe in the two-dimensional space here, x1 and x2 here, and in this case you have three classes of data sets here, they cannot be linearly separable, especially between red and green here. Green and red cannot be linearly separable, clearly. Maybe once you introduce the third features, x3, if you plot the data in a three-dimensional space, x1, x2 plus x3, it might be possible that the green dots are now become separable from the red dots. So that may be possible. So the idea is to include more features. So second possibility is this, we go beyond using a more sophisticated model. Instead of using linear models here, we might say, well, let's build a nonlinear classifier. So in that case, you might be able to separate these two possible choices of that. So, or another possibility, we just say, well, we just happily apply the linear models here. We are willing to accept certain errors here. So which means that I'm willing to accept the fact that I will not be able to perfectly separate all the data in the training data sets here. I will be happy to have certain errors as long as the error is not too large. So that would be third way to address this type of problem here. In general, modern days more or less stick in these regimes here. I'll be happy to accept certain errors. So always, in practice, it's almost impossible to try to come up with a classifier that produces zero errors. And then in many cases, whenever you're able to do that, in fact, that's probably not a wise choice. So we'll come back to this point here. So,
Professor, I had one question.
Yes.
So you mentioned that usually it's very difficult for us to get data that is linearly separable. But even if we have data that is linearly separable, it could be possible, right, that our classifier is not perfect because the data might not be a correct representation of real world.
Yeah, that's correct. So we're going to talk about these type of issues here. So the question is, even if the data set is linearly separable, which classifier should I choose? Right. So if I have a classifier achieve the perfect classification on the training data sets here, am I happy with that classifier? And to what extent this classifier will do well on unknown test data sets? So we're going to come back to this point here. That's a good question. So for instance, in this case here, I just want to show you some of the examples here. In this case, it's not linearly separable two-dimensional data sets. Here, you cannot find a line to separate blue dots from red dots. However, we know that if you use the k-nearest neighbor approaches here, you can derive this kind of nonlinear, more complex piecewise linear decision boundary such that you can separate them here. So you can always say, well, if it's not linear separable, maybe I can go to more complex models. It's always possible to do that. But the question, is this better than the previous one? So that's a question we should be able to answer. And right now it's not clear. We have to do test, cross-validation testing. Right, so the perceptron, to go back to the perceptron, the model we talked about here, it's a linear models here, but we just make decisions here based on linear combinations input here. So in general, so the perception algorithm was proposed a long time ago, was initially proposed in the 50s here. And then people quickly realized that the perception algorithm cannot separate linearly non-separable data sets here. And then there one example people used again and again in this field is using this XOR as an example. So we'll plot in this side here. So in this case here, suppose you only have two features here, X1, X2 here. And then also you assume that your input feature here is binary. So X1 can either be 0 or 1. X2 can only be 0 and 1 here. So as a result that you only have 4 combinations. You don't have that many combinations here. X1, X2. So these are all combinations of X1, X2 here. And this is a predictive model. Essentially, in this case here, Y is a logic AND operation between X1 and X2. So this is called an AND operator here. So we plot in this side here. So this will be blue represent -1, -1, -1. This will be 1 here. So if both of them are 1 in the fourth row here, and that would be Y will be predicted to be 1 here. So that is the AND operation. So for this type of 4 dots, and you know that they are linearly separable. I can put a line, I can separate them here. But there's another operation here called an XOR operation. XOR operation. So XOR operation saying that if this X1 and X2 are the same, they will give you a 1. Otherwise, if X1, X2 are different, they give you a -1. So this is called an XOR operation. So within the XOR operation, you can see that those 4 data points are not linearly non-separable. You cannot find line to separate these 2 group points. And this kind of the XOR model shows you the failure, shows you the kind of failure of perception algorithm, or it shows you and how poor the perception algorithm is in practice. Whenever you have this, even this type, relatively simple type of data set, so the perception algorithm will fail. And then there is this great AI researcher called Marvin Minsky. He was a professor at MIT. He was a founder of the AI lab at MIT. He wrote a book called Perceptron. So with a co-author, he just wanted to make a point that the neural nets have limited power because it cannot even solve XOR problem. So he wrote the book in the 60s, I believe, and because of that book, a lot of people just left the field because they think that, well, even XOR problem cannot solve it. Why should I bother with the perception algorithm? So a lot of research left the field because of that book. He's very influential at that time. The example he used in that book is this XOR problem. You can see that the perception algorithm cannot solve XOR problem because the data now is not linearly separable. And how do we handle that? So I talked about we can use nonlinear decision models and go beyond perception using nonlinear decision models. So that's one thing we can talk about in the future. But for now, another idea you can use, you can augment your features. As I mentioned in the case of linear regression, and we said the linear model is not really linear, and the predictive model is linear, but instead is linear with respect to the parameters. So that's the key things we talk about. So the idea is that, well, in order to generate nonlinear predictive models, what I can do is to introduce nonlinear features by augment those input features of that. So that you can do similarly for this type of linear classification models. So for instance, this is the examples here to illustrate that point. Suppose you only have one-dimensional samples here. You only have 1 feature. That's your X1 here. So within this one-dimensional features here, and then you have 3 dots here. You labeled with a 1 here or +1 here, suppose, and you have blue here labeled with -1 here. You assign two different class labels to that. Of course, for this and eight samples here, you cannot have a linear decision boundary. And remember that for one dimensional, there's a linear decision boundary. Essentially, just cut off at one point here, right side with one label, left side with another label. So that you can see that you cannot draw a decision boundary, with a cut on the line to perfectly predict those two class labels. Of that. And however, one trick you can do is that you can introduce one more features. So that feature, one more feature you can do is using this kind of quadratic features here. So instead of x1 here, so this still along this side here is still x1, okay? But I'm gonna introduce one more features along the vertical domains of that. Suppose that's x2 here, and then you choose x2 to be x1 squared using this additional quadratic features. Well, so what happened here? Suppose this is around your zero origins here. Suppose around origins here. And if you use x2 squared, and then you pull up those blue dots in this way, the blue dot this way here, and then red dots along these regions of that. So now, with these two features here, x1 and x2, and now this is the new representation of the samples in the two-dimensional space. So in two-dimensional space, you can see now that, well, this then now can be linearly separate because I can simply draw a line between here. And that you can see can separate blue from the red. And now it becomes linearly separable case of that. So you can see that, so by introducing features here, you can derive nonlinear decision boundary. So more specifically, if you want to look at the decision boundary within the one dimension here, you might have decision function to be threshold of this quadratic functions here. Instead of previous linear terms here, you have this x squared. So x squared would be the x2 features, the second features of that. So now you have decision boundary, look something like this. So that's just keep in mind that in the context when we talk about this linear decision boundaries, you can always have nonlinear decision boundaries by introducing more features, nonlinear features of that. Okay? So that's so for instance, you can solve the XOR problem by introducing one more features of that. So, and for instance, if you're introduce quadratic features here, and then in that case, you can have a decision boundary to be like ellipsoid here instead of a straight line. So under that context, you can solve the XOR problem by introducing one more features here. You should not only using x1, x2 as features here, but also use x1 squared, x2 squared, and x1 times x2. Introduce these three additional features. So in that case, you can learn a decision boundary. And then the decision boundary will look like an ellipsoid because now you have a higher the quadratic features of that. So the idea is what? So we can still solve XOR problem using perceptron by augmenting the existing features, but you have to use the augmented feature, otherwise you won't be able to separate them. All right, so another thing I want to comment on in this, how do you represent the features here? So in many cases here, just like in the linear regression cases here, in many cases the features itself is categorical. They're not necessarily always this continuous number. In many cases here, they provide, in real applications, what you see are those features representing Excel files. For example, very common, you might be see many discrete features. For instance, this is kind of one example of the discrete features here, say, what the shape of the surface of the mushroom here, and you might want to predict the types of mushroom based on this description you have here. So think about that as a classification problem. But your input features, and it might be represented by this categorical discrete features here to be said fibrous, grooves, scaly, and smooth. So you have 4 different types of surface features here. The question is, how do I represent those features here? Well, probably, you might incline to choose to represent these features using these numbers here. Say, this is 1, this is 2, this is 3, this is 4 here. Using this continuous number to represent these features here. And then, well, that's okay. However, when you use this continuous number representing the features here, you inherently assume there is this kind of ordering information assumed within the features here. So because we're doing linear combination, so this will be features here. Later on, you're going to put a theta times x here. So that will be the linear response came from this individual features here. Because you assign 1, 2, 3, 4 here. So essentially, if your surface is described by smooth, you're going to give a higher score than the surface described by fibrous here, if theta is positive. So as you can see now, inherently you assume there's some ordering information associated with the surface features here. But although in reality, and you might those features just they're categorical features here, there's no any ordering information associated with these categorical features. So a better way to represent those features here is instead using this new representation here. So you might want to use this 4 numbers to represent this one feature here. So again, this is only one feature, right? However, you might want to use 4 numbers to represent these features here. You might represent these features here to be 1, 0, 0, 0 here. And you represent this feature to be 0, 1, 0, 0. This to be 0, 0, 1, 0. And this to be 0, 0, 0, 1. And so in this case here, in order to represent this feature here, the number of parameters associated with the feature will be 4 instead of 1. So because now each feature you have the 4 numbers here. So I need to assign what are the numbers associated with each individual feature. You might have theta 1, theta 2, theta 3, and theta 4 here. So essentially it says this. So if I have a feature associated with the fibrous character feature representation here, and then the score will be theta 1. If I have another feature, say it is smooth, and then the score calculation will be theta 4. And so now you have more kind of representation in the parameter choice associated with these features here, because I do want to differentiate these 4 different features here. There's no inherent ordering information associated with this feature. So because of that, I'm going to try to learn this 4 number instead of 1 to calculate contribution to the score from these features here. So this is something to think about, because in practice we do encounter this type of things very often here. How do you represent those type of categorical features here? And this is the example that this categorical feature, there's no order information, but there's some other cases that do have order information. For instance, you might want to separate age into different groups. You might say between 0 and 18 to be one age group, and then, between 18 and then 18 to 40 to be another age group, and then 40 to 50 to be another age group, and so on, right? So you might have something like this right here, and then 50 greater, and then to be another age group here. And the question in this case here, and how are you going to represent this categorical features here? Well, so that's kind of more debatable. And you can use 1, 2, 3, 4 to represent these features here. If you believe the things you want to classify here, and it's kind of have this type of linear correspondence, associated with this ages here. But however, if you believe the things you try to predict here, it doesn't necessarily assume any ordering information here. It's just say a different group responds differently. So in that case, you might want to represent those features here using this type of so-called 1 out of k representation instead of this continuous number representation. So this is a side thing. Just keep in mind when you represent those things here. Just keep in mind that you have to choose those representation, carefully. All right. So now let's get back here. This is all related to questions here. Well, if that is not linearly separable, and then I can increase the number of features. And then we know that typically data is easier to separate in a higher dimensions, because in higher dimensions the data tend to spread out. So because of that, it can be easier to separate in higher dimensional space if you augment, increase more features. So eventually you will be able to separate all training examples perfectly even using a linear classifier here. So however, and now the question is this always a good choice or not? So, now you have to go back to the things we talked about. It's always the choice of the problem, the predictive error as a function of the complexity here. When you increase more features here, you increase complexity of models here. And as a result that your training error will reduce as a result of this. However, the performance does not necessarily always decrease on the test data sets here. So we have to evaluate this choice based on unknown test data sets. And in the end, we choose the ideal range, the ideal number of features to use for that particular problem. So this diagram, you should always keep in mind that how to choose the right range of the complexity for solving that particular problem. All right, so this is the perceptron here. What we talked about so far is this. Perceptron is simply a linear classifier here. The decision boundary is linear here. And then we talk about what type of problem can be solved by perceptron. And it only can be solved when the problem is linearly separable within a given features. If they are not linearly separable, you have to augment the features in order to apply perceptron algorithm back. And okay, that's the perception algorithm. So, however, there's one problem I have not talked about, is how to identify the parameters, learn the parameters of the perception models. I talked about the model itself. The key thing is how do we learn those parameters of that? So that's I'm going to talk about next year. How do we learn the perception here? So there are multiple ways of doing this. So right now, in general, when we talk about our framework here, we always say, well, now we have the data, we have the model. The next thing what we should do is to try to come up with a loss function to describe the performance of our model here. And then later on, I can minimize this loss function here with respect to parameters here. So as a result, I can convert the problem into an optimization problem, and hopefully I can apply optimization algorithm to identify the right parameters. So the question, what would be the good loss function for the linear classifier? So right now, so we talk about the performance are in terms of the classification accuracy. So most of the natural one here will be simply say, what is the error rate of my classification models? So error rate is simply calculated as the fraction of the samples that are misclassified. So what this means is you can represent this with the indicator function here. So remember, this is my predicted score, suppose this is my predicted labels here. So suppose this is my y hat here, y hat with I samples here. This is predicted labels. This is the ground truth labels here. So I'm going to, for each one of the samples here, I'm going to check whether my predicted label is the same as my annotated label, ground truth label. If it's not, that counted as one mistake. So I'm going to sum over all the mistakes that I have divided by total number of samples I have. So this will be the error rate of my model. Right? So fractions of the predictions are incorrect. This is my error rate here. So this guy here will be between 0 and 1. So 1, which means you completely wrong. 0 means that you are doing perfect classifications. So this is the kind of one metric for measuring the performance of linear classifier. So in terms of the error rate or in terms of the accuracy. So 1 minus error rate would be accuracy then. So however, this, and now you might think, can I use this as my loss function? It turned out that's kind of very hard to do. Why is that? Because this error function here, they are all kind of thresholding functions here and a binary thresholding function here. As a result of that, it's very hard to calculate the gradient of this error function because they are just simply thresholding here. And now if you look at the gradient here, these are all 0, 0. And then in the middle here, there's a jump and there's not differentiable. So you can see that there's no gradient information, either 0, 0 or does not exist. So in that case, it's very hard to do that. So, so as a result, it's very hard to train a gradient descent based algorithm, try to minimize this error functions here, and because they're not differentiable. So it's not a very good choice and as a loss function. Well, it's a good choice for measuring the accuracy of the model, but it's not a good choice for use as a function for loss function. And so we need to come up with something else. Well, so another choice you might think, well, can I use MSE as my loss function? So right now I have my predictions here. So prediction, suppose I'm going to use this my prediction here, the theta dot x here. And this is a linear response as my response here. I simply say I'm going to calculate my y here. So it's my labels minus this guy here, take square root of that. Can I use this as my loss function? This will be pure MSE-based loss function. The only difference here, this guy here is binary now, -1 here. And this guy here is continuous numbers. So it turns out this is going to be a very bad choice for loss function as well. So why is that? Well, suppose you have this model here in one dimension here. So right now, so you have the 4 data sets here, then another 4 data from another labels here, and then that's your linear response here. So, and then you can make a decision boundary at this point here. Essentially, at this point here, this is decision boundary. This will be a +1. This will be -1 here. So that would be a good one. For now, let's assume if you add one more data to this existing data set here, you introduce one more data set here. So this is a, more or less like not outlier here. Essentially, way in the positive regime. So in this case here, well, if you are using your existing model here, your existing decision boundary here, this one will be totally fine because they are on the right-hand side. You are doing the correct predictions. That will be okay. However, so now if you calculate the difference between this models here and this data set here, right? In the initial parameters here, so that will be your residuals. This is from linear model. This is your labels here. So there are big residual between your theta.x here. This is this guy's here, and then this labels will be +1 here. You can see you're going to encounter big issues because the big residual here, if you use MSE as your loss function, you will be forced to reduce the gap between this prediction here, which means that you have to tilt your lines in this way here. If you tilt this line here, what happens? Then you have to shift your boundary to the right-hand side of that. You can see in practice, and this will not be a good choice for the loss function. All right, so what can I do? Well, so before I talk about the introducing loss function here, I'm going to talk about the algorithm first. So this is kind of non-conventional, but this is how this was introduced initially for the perceptron algorithm. So perceptron algorithm was people proposed the perceptron classifier. They first talked about the models. They also talked about the algorithm for identify the parameters of the model. They didn't talk about how the algorithm was derived. So that piece is missing. But let me introduce the algorithm first. So this is the perceptron algorithm here. It's something like an online stochastic gradient descending algorithm. So the algorithm is doing something like this. So you're gonna iterate through here, through these steps of that. So iterate until the algorithm converges. And then within each loop here, you cycle through each data point j here. So within each data point here, you make predictions here. And what you do, you calculate the score, dot product between parameter and your samples here. And the next, you take a threshold function, you simply take a sign function. That will be +1 or -1. So this will be your predicted labels. And they'll be either +1 or -1. And then next, you're doing something like this. You calculate the difference between this is your targeted values minus your predicted values. So this will be difference, right? Difference between your targeted value and your prediction. And then you take the difference times this xj here. And then use these guys here to update your parameter. With this little coefficient in front of that, there will be alpha here, it will be constant. If you look at these guys here, it looks very familiar to you, right? Because this is the algorithm looks very familiar to the online gradient descent algorithm we use for linear regression. So they refresh you. In the linear regression case, what do we have? We say this, we're going to calculate this delta theta here to be the negative of the gradient of the loss function. In that case, is MSE with respect to the parameters here. And then we said that for one sample, the gradient of the MSE, the square function with respect to theta, is this. It's the predicted values minus the observations here times this input x. And this is a residual. This is, we call it a sensitivity parameter. Essentially, the x, because the loss function, the prediction is based on x times theta here. So the higher the x here, it is more sensitive to change on the underlying parameter theta. So that's kind of sensitivity. But more or less in this form. So which means the updated delta theta here, in the end, will be the y minus prediction times x. So that came from the linear regression case. If you recall that. So look, now this is online linear regression, online stochastic gradient descent, SGD. So which means that updated parameter based on one sample only. If you look at that, if you compare these two, they are the same. In terms of format, they are the same here. This is a target value, this is prediction here, difference times the sensitivity vector xj here, and use that to update my parameters here. So now look at this guys here. Now look at this guys here. Well, because y here are categorical, both of them are either -1 or 1 here. Essentially now, there are two cases here. So first of all, if y predicted y hat is equal to y, which means you are making the correct prediction label assigned is the same, and then the residual is 0. So if that's the case, residual is 0. So with residual 0 here, there's no update. You don't need to change the parameter theta. And then you only change it here when residual is not 0, which means that you can either to be +2 or -2 here. Keep in mind that in this case, both prediction and target value can only be -1 or +1. So only choice for the difference between them can only be +2 or -2. So for instance, if your target value is 2 here, but you predict to be -1, so overall, this residual here will be +2, right? So in this case here, you will update your parameter. So essentially what they say in this, right? So when I apply this so-called perceptron learning algorithm, so I go through each of the data samples here, and if data samples already predicted correctly, in that case, I will not update the parameters here, and I will update the parameter on those samples here that are incorrectly labeled. So, and then what depends on these guys here can be positive or negative, right? Can be +2 or negative here. And then I will update the parameter theta differently. So now let's look at one special case here. Suppose my predictions here is 1 here, is -1 here. Suppose that's the case. But actual observation is 1. And so of course, there's an inconsistency between prediction and observation. So now y minus y hat is going to be equal to 2. So this would suggest that you're going to change the parameter, the delta theta will be roughly proportional to 2 times x here. So why this is the case? Why this will be 2? Well, let's think about this way. So your target value is 1 here, but you predict value to be -1. Essentially, you are undershooting your prediction. You are not predicting as much higher value as you hope to be. So how do I produce a higher score? Well, in order to produce a higher score, I'm going to change my delta theta to be 2 times x. Well, now, remember that x times delta theta here. So this will be increment in the score after you make this change here. Now it becomes 2x squared. You can see now we increase your score. What this will be consistent with what I see so far, because my prediction here predict to be -1. Instead, I should be +1, which means I should increase the score. So what if you do this update, it will lead to that desired effect of increasing your score. You can see it's along the right directions of that. So this is the perceptron algorithm here. You're running very simple, go through each data samples here, you update the parameters here, and then that's it. So this algorithm looks very simple here, looks very simple. And it looks like something like a stochastic gradient descending algorithm here, and it's driven by that. It probably wasn't originally motivated by this. You're gonna run through the data sets here, and then if the algorithm and didn't converge, you can run that again. So you can cycle this again here. And in the end, eventually, so this algorithm may or may not converge, because right now we have not demonstrated that. So this is a, so it turns out that, so people have studied the behavior of this algorithm, and they can show that this algorithm will, by the way, before I state the result here, let me make one fun fact here. So that, well, let me say this, make a statement here. So this algorithm here will converge within a finite number of steps. So this is a very strong statement. If the data is linearly separable. So this is a statement, and you can actually prove it. So this perceptron algorithm will converge within a finite number of steps, which means, well, if you run this iteration after, not infinite number of steps, well, finite step, the algorithm will actually stop. So when do you think the algorithm will stop? Well, if I have parameter theta now, can already correctly separate these two classes of labels. You can see in that case, this is always 0. Because already my predict level is always the same as the actual target level. So in that case, you can see that you're running through entire data set, there's no single update of the parameters. So you will stop your algorithm, because even if you're running continuously, there's no update anymore from that point. So the algorithm converges after that number of steps. So this is saying that you can actually prove that if you choose alpha not to be too large, and that's something you can put a threshold on that, and then in that case, this algorithm will converge after finite number of steps if original data is linearly separable. But what happens if the original data is not linearly separable? Well, in that case, your algorithm will running infinitely, running continuously, will not converge. So this algorithm, in some way, is limited in the sense that the algorithm will not converge if your data is not linearly separable. So, however, if you happen to have linearly separable data sets, and then the algorithm is good, because it will converge within only finite number of steps. So remember that for the gradient descending algorithm we talked about previously, there's no such thing say that the algorithm will converge within the finite number of steps. There's no such thing. The algorithm will asymptotically approaching the solutions, but always asymptotically approaching the solutions, right? The error becomes smaller and smaller. So you cannot actually put how many steps I need to run there, because it depends on the accuracy of your optimization procedures, right? The higher accuracy you demand will run longer time. So in this sense, the gradient descent algorithm is very different from this perceptron learning algorithm here. I just want to make a comment. So this algorithm was very exciting. And so a lot of people are so excited that they actually designed hardware to implement this perceptron algorithm. So that was the think about this is a very long time ago, 50s. And Rosenblatt et al. They designed this perceptron algorithm. They get so excited by this algorithm here, they design more hardware for doing that. They even computer for doing that. So there's a lot of enthusiasm about this algorithm here. So this is a historical reason I introduced this algorithm here. However, so far you still kind of wonder about this algorithm here, because this algorithm, there's no loss function. And somebody came up with this kind of algorithm based on intuition, and I think, well, that doesn't make sense. The algorithm, if I update it this way, that seems like it can lead to improvement performance, but it cannot show that the algorithm is optimizing some kind of loss function. So that's not. So next I'm going to talk about here. So what type of loss function I can put on this algorithm here? So there are multiple ways for doing this. First of all, I'm going to talk about something called a surrogate loss function here. So in this case here, I'm going to introduce something like an MSE loss function. But it's different from the previous MSE because I cannot calculate the difference between my target values and the linear response, because that needs two problems of that. So one way of doing this is this. So I'm going to calculate the score functions here, the score here, theta here, dot x here, this linear response, and then I want to compare this with the ground truth observations here. So I want to calculate the difference between them. Previously, I'm using something like this, right? And we said that this MSE loss is problematic because is very sensitive to data away from the boundary. Well, so one thing I can do, I can apply a thresholding function here on the response function here, some kind of nonlinear thresholding function. Well, something like a thresholding function, but I have to make it smooth, right? And if I have a thresholding function, that would become the error rate of my models here. However, if I want the function to be kind of differentiable, I'm going to provide a smooth versions of the thresholding function. And that's something we can introduce one type of function called a sigmoid function for that purpose. So the theta function here. So this theta function is this. So now I'm going to actually change this notation here and assume my target value now is between 0 and 1 here. And for that purpose here. The reason is this. So I can design a threshold function to be something like this one here. So depending on score here, this is score theta dot x here. So this is a 1, and I'm going to bound this score function between 0 and 1 here, right? When it's very positive, it is close to 1. When it's very negative, it's close to 0. So I have this function here called a sigmoid function here. And when it's positive, very close to 1. When it's very negative, close to 0 here. Essentially, this is something like a thresholding function, but now when my threshold is between 0 and 1 instead of -1 and 1. The reason I do that is just because this function is bounded between 0 and 1 here. And for that purpose, what I can do correspondingly is to change the target value from -1 to 1 to 0 and 1 here. So as I mentioned at the very beginning, this is just for the notational purpose here, because this is categorical. It can sign to be using convention 0, 1 or -1, 1. So it depends on different content. But now let's using the notation 0, 1 here. So my theta here is this type of a sigmoid function here is bounded between 0 and 1 here. When it's very positive, it's 1, it's very negative 0 here. And then I'm going to compare, essentially this is my prediction here. My prediction now is kind of a smoothed version of the prediction. It's not a thresholding function here, right? So threshold function will look something like this. When it's negative, it's 0. When it's positive, you go like this guy here. So this is my prediction function here. However, I'm going to find a smooth versions of this kind of jump function here, and such that the transition will become smooth. And then here is 1/2. And this is so-called sigmoid function. And then next, what I can do is I can calculate the difference between my target value and this sigmoid of the scoring function, the linear response function here, and then take the squares of that. And that can be treated as a loss function. And in this case here, because I do not have thresholding function, so the function here is differentiable. So I can apply the gradient descending algorithm to calculate the loss function. So we're going to talk about the later on part of that. So let's look at some of the examples here. So this is one example here in one-dimensional case. So this is the thresholding here from left to right here, thresholding here. But now I'm going to, once I calculate score here and then change that, update that with this sigmoid function here. So from this side here, it will be close to 1. From this side, it could be 0 here. And now you have this ground truth to be 0 and 1 here. So you now calculate the difference between these two is highlighted in the green lines here. The green bar here will be representing the residual between your predicted soft versions of the threshold function and your target values here. And along this extreme point here, they're close to 0 because they're very close, because your sigmoid function is very close to 0 and your target value is 0. So the difference is 0. And similarly, on the right-hand side here, that will be very different, will be close to 0 as well. Only see difference along the decision boundary of that. And if you try to minimize this guys here, and then that will be the place you can design the optimal decision boundary of that. So that's in this type of the loss function. So the reason that this type of loss function, that what to think about here. So why we need this type of loss function here? Well, so let's think about it here. So in the case of the perceptron learning algorithm, and suppose we have this example of data sets here. So this data sets here illustrated in this picture here, and you have green, and blue, and red dots here. For this type of data sets here, you can see that this data set is linearly separable. So which means the perceptron algorithm can find a solution and it will converge within a finite number of steps. Okay. So now it depends on where do you initialize the parameters. The perceptron algorithm might end up with these solutions here or with this second solutions here. And in both cases, you can see that in both cases here, they give you 0 classification error on the training data sets. And you can see that the perceptron algorithm will stop whenever you find this, when you reach this solution or this solution here. They will converge perfectly happy to end this point here. So in fact, it's very common for perceptron algorithm to identify these solutions here on the left side here. Well, the question is this: between these two solutions, and which one do you willing to accept? Which one do you think is better? So that's the question that something you can think about here. So even though these two cases here, both of them can perfectly classify the training data sets here. But however, you might wonder how does this decision model will perform on unknown test data sets. Well, based on this type of representations of data sets here, you might have a good guess to think that the model on the right-hand side will do better. So why is that? Well, you think about it here. Suppose my test data set came roughly from this distribution here. Well, and it would be reasonable to add some red dots here, right? And it would be reasonable to add some blue dots here because they are close to the cloud of distributions here. That would be okay. But now you can think about this new test data sets here, and the model on the left side here will make mistakes. However, the model on the right-hand side here will still make no mistakes on those new test data sets. As you can see, you might have a good guess to think that the model on the right side will do better on unknown test data set. We say it will generalize better. So you can see well, perceptron algorithm will be happy to identify any one of them here. And perceptron algorithm itself will say both of them have 0 error rate and they are equally well. However, we know that probably the right-hand side of the model is better. And the question is, how do we do that? Well, if you use this type of loss function, it will give you a better solution to that. And hopefully identify solutions on the right-hand side. All right, so the question is, how do we identify the correct parameters here? Well, the thing is, once I do this guys here, and then I apply gradient descending algorithm to learn the parameters, the models of that. So is this one here. So the MSE-based loss for the classification models here. So I have this sigmoid function. Let's first define the sigmoid function here is equal to 1 plus E minus Z. So that's the function it's called a logistic function or sigmoid function. And this function here with these values between 0 and 1, 0, 1 here, and then with approach to 1 on the right-hand side, approach to 0 on the left side of that. So this will be Z here, and that's the sigmoid function here. In the middle, this 1/2. And what do we say now for the binary classification? Suppose we're given one pairs of data sets here, one data set here, and now we're going to use this notation here, y is either 0 or 1, using my notations of the labels. So it's not using -1 or +1 here. So that's my notation here. And then my loss function is this, is saying, well, theta dot x here, this is the linear response here, apply the sigmoid function to squeeze to bound the values of these functions here, so that those response here now is going to be between 0 and 1. So now more comparable to the target value. So next I'm going to calculate the difference between this sigmoid transformations of this linear response and then to be a y here. And then this will be take square root of that. And that's going to be my loss function, okay? And divided by 2, well, this is the coefficient in front of that. And then, so this is for one sample. And for multiple samples, you can average them. In the end, you have this loss function for all the samples. And what do? You have these functions of the parameter theta, and then you're going to divide by 2m here. Summation j goes from 1 to m, and you have your your target value, and then theta dot x here, your J's input here, and the sigmoid transformation, and take a square root down. So this will be overall your loss function, MSE loss function, after you introduce this sigmoid here. And that's the only trick you use here. And after that is very similar. You can apply MSE to this function. And then what you do next is this. How do I calculate the update my parameters? And now for that purpose, what I say is this, what I need to do is to calculate the gradient of the loss function with respect to parameters. And we need to calculate the gradient of this J function with respect to parameters here. How to calculate this guys here? Well, let's look at the one loss function here. Loss here equal to 1/2 y minus the theta dot x here. And use this as an example here. Well, this is simply a quadratic functions of the sigmoid functions here. What do? You calculate gradient respect to my loss, respect to parameters here for this one sample. And first apply the chain rule. Right? So apply the chain rule from the calculus. So you calculate respect to this quadratic function first, and then with the quadratic function, apply these parameters to that. So if you carry out this calculation, that will be this, right? And then first quadratic function will be simply the linear functions here, theta dot x here, minus y here. So that's be quadratic terms of that. And then calculate the derivative of this sigmoid function respect to this function here. And then next will be the linear function with respect to parameter, that will be x here. You can see that is the gradient with respect to parameter of that. So again, as you can see, you treat this as if it's your prediction here. This is your target value to that. This is still be called residual terms. All the errors, right? And then this is the sensitivity here. X is the sensitivity. So the only difference is always a residual times sensitivity. The only difference now you have this additional term to be the derivative of this sigmoid function and then plug in the values of this response here. And that's something you need to calculate here. However, it turns out for this sigmoid function, this function I talked about here, and then it's a derivative, it's actually in relatively simple form. This function here, if you carry out this derivative calculate this apply your calculus, you learn what your calculus, you calculate it by yourself. That is simply theta z times 1 minus theta z here. It's kind of in relatively simple forms of that. Okay, if you use this fact, and what do you get in the end is this, right? So this guy here is simply equal to theta x here times 1 minus theta x, sigma theta x here. And that's it. If you already calculate this sigmoid function, the response here, you can treat these guys here as if it's your predictions here, right? You can say, well, let's put the y hat here, treat this to be theta, to be softer versions of my predictions here. You like this guys here. And then this gradient here was simply equal to, prediction minus your target values. And then times this y hat times 1 minus y hat. This came from this guys here, and times this input parameter here. So essentially sensitivity has to be modulated by this y hat times the 1 minus I hat here. And then after you're doing that, well, then that's it. And then this will be your residual terms of that. So by doing that, you're able to calculate this gradient of this loss function with respect to parameters. And then once you do that, and then you know how to update the parameters using the gradient descending algorithm, now go back to what we talked about previously. Okay, so that's for this type of MSE loss functions here. And this is but however, I should mention that this is just only one way of introducing this loss function here. This is based on MSE versions of that. And so in the next lecture, we're going to talk about a second methodology, a second way of impose a loss function on this particular problem. And the second method is more popular than this one here. This one you can use it, still good, but I think that the second version, the loss function I'm going to introduce on Wednesday is more popular, but it's based on a statistical consideration. But I'm going to talk about it on Wednesday. For now, I just want to kind of review what we talk what we talk about today, right? So we talk about binary classification, particular linear classification, and the model is very simple. The question is how to learn the parameter from the models. And then we talk about the algorithm based on perceptron algorithm. So the algorithm, and then next we talk about the algorithm, a gradient descent based algorithm based on this type of a loss function introduced through MSE, but based on this softer thresholding functions of the linear response, and then compared to the target values of that.